Okay, so a rational function is a function in which you've got a fraction with an x in the bottom. It could be as simple as 1 over x, or it could be some kind of an expression in x on the top and an expression in x on the bottom. Any kind of fraction that's got variables in the denominator is what they mean when they're talking about a rational function. So it's got a polynomial in the top and a polynomial in the bottom, which the polynomial could just be a 1. The denominator, though, typically would need to have a variable in it. If we graph something like just 1 over x, notice that the domain of this is that x cannot equal 0. So if we were writing that in interval notation, if you look at it on a number line, every number except for 0 would include all the numbers below 0, from -infinity to 0. Make sure that's a parenthesis, so that the whole point is to leave out the 0. And then we've got all the numbers above 0, so from 0 to infinity. So this is how you'd write all the numbers except for 0. So there is no value allowed at all where the x is going to equal 0. We can have numbers bigger than 0. So 1 over each of these, 1 over 1 is just 1, 1 over 2, 1 over 3. If we put in numbers smaller than 1, but between 0 and 1, numbers in here, if I put in 1/2, 1 over 1/2 is the same thing as 1 times 2 over 1, so that's just 2. What this function actually does is simply inverts the x value to get the y value. So say 1/10 would be 10. 1 over 100 would give us 100. So if I look at these points, I've got 1, 1, 2, 1/2, 3, 1/3, 4 would be 1/4. This is going to flatten out. Sometimes we'll write this in terms of as the x values go toward infinity, as the x's approach infinity, the y values are actually going to approach 0. As your x's get bigger and bigger and bigger and bigger, your y values are going to get smaller and smaller and smaller. 1/10, 1 over 100, 1 over 1,000, 1 over 1,000,000. So as the x approaches 0, and I'm talking about from the positive side, so as we're talking about x's in between here, the y values are getting larger and larger and larger. So 1/2 gives us 2. 1/3 gives us 3. 1/4 gives us 4. So they're going up like this. So as x approaches 0 from the positive side, y approaches infinity. There is no x-intercept because x cannot be 0. Or sorry, there's no x-intercept because y cannot be 0. There's not going to be any x-intercept because there's no value that would make 1 over x equal to 0. The only way a fraction can equal 0 is if the numerator is 0. This is important to remember. The only way a fraction can be 0 is if the numerator of the fraction is 0. And since this is just a plain 1, no matter what x is, the top is 1. So y cannot be 0. We already know that x cannot be 0, so there's no y-intercept. So the axes actually create a framework for where this graph is. Now, if my x values are negative, then I've got 1 over a negative number, which is going to get inverted to be the y, which 1 over a negative is still negative. So all of my negative x values will give us negative y values. I don't want this to look like it's going to actually hit the y-axis, because it won't. So this graph is broken up in 2 separate curves, one to the left of the y-axis and one to the right of the y-axis. One above the x-axis and one is below the x-axis. Got the picture? Now, if we look at how the transformations work, what if we looked at 1 over, say, x minus 3? This graph moves 3 units because I'm changing the x value before I'm doing the main function, which is 1 over that. This is a horizontal, and the horizontal is backwards. I could write this as 1 divided by parentheses, x minus 3. So it's basically in the parentheses. So this moves 3 units to the right. Notice that the domain for this is going to be that x cannot equal 3. So in interval notation, we would write from negative infinity to 3, and then from 3 to infinity. So the graph here moves 3 units to the right, 1, 2, 3. I'm going to put a little dotted line in here. So now the graph looks like this. Three units to the right. Now, this line, where basically the y-axis got moved over 3, this is called a vertical asymptote. Asymptote. It's got a P in the middle of it. An asymptote, a vertical asymptote, is a vertical line along which the graph will flatten out. That's an L. But never reach. So as the x values get close to, in this case, x equals 3, the y values are forced to either go to positive infinity or negative infinity. They're going to get pushed up or pushed down. See, again, this fraction can never equal 0, because the only way for a fraction to equal 0 is for the top to be 0. It's not going to happen. This also has a horizontal asymptote. A horizontal asymptote is a horizontal line along which the graph will flatten out as x approaches infinity or x approaches negative infinity. So as your x values get really, really big, it's going to flatten out along it, in this case above it, because they're positive values. So it gets closer and closer and closer. Here, as x goes into negative extreme values, it's going to flatten out along it, but when x is negative, x minus 3 is negative, so a positive 1 over a negative is going to be negative. So all of the y values are trapped below the x-axis here. So these are your asymptotes. The asymptotes in a rational function are absolutely essential to being able to figure out where the graph goes because they frame it out. But they put them in as dotted lines because they aren't actually part of the graph. As a matter of fact, there literally is no value in this graph where x equals 3. So those are put in as a dotted line. So putting x minus some number is going to move the graph to the right. Putting in x plus some number is going to move the graph to the left. Now, what would cause the graph to go up or down is if you take the 1 over x and you add a number. Let's look at what that would do. If we looked at the graph of 1 over x plus 3, we know this is going to move up 3 units. However, they're not going to give it to you like this. They're going to get a common denominator and push them into the same fraction. So if we take the 1 over x and we add 3 over 1 and get a common denominator, which would be x, then we get 1 over x plus 3x over x. And if I write these terms in descending order, I would get 3x plus 1 over x. Okay, so this would be easy to recognize as a g that moves up 3 units. This is trickier. Let me show you how to figure out what that's going to do. If we look at it, it's going to take this graph and move it up 1, 2, 3 units. So it's going to look like this. Now notice that we've got this 3 right here, which came from taking this 3 and getting a common denominator. So the coefficients here are 3 over 1. And that is exactly how we find where a horizontal asymptote has been moved. If we put in larger and larger and larger numbers here for x, if I let x be 1, this would be 4 over 1 is 4. If I let x be 10, this would be 3 times 10 is 31 over 10, which is 3.1. If I let x be 100, this would become 301 over 100, which would be 3.01. If I let x be 1,000, this would be 3,001 over 1,000, which would be 3.01. So you can see that as x gets bigger and bigger and bigger, this 1 actually takes on less and less and less of an amount of influence over the y value. And it's actually approaching 3. So as x approaches infinity, the y values are going to approach 3. So you can see that that does work here. If you're looking for the horizontal asymptote, for the horizontal asymptote, turns out to actually be really easy to figure out how to do that. If the degree of the numerator, remember that the degree is the exponent on the term that has the biggest exponent. If the degree of the numerator is smaller than the degree of the denominator, then the horizontal asymptote, I'm just going to abbreviate that, is going to be y equals 0. That is the equation of the x-axis. If the degree, that's supposed to be an e, of the numerator equals the degree of the denominator, and y equals, let's say we've got something x and something x down here. And for the degrees to be the same, they could both be x's, they could both be x squared, they could both be x cubed. You could have 2 terms on the top and 3 in the bottom, but as long as the exponents are the same, then the horizontal asymptote is simply going to be the leading coefficients from the top and the bottom. So it's going to be the equation y equals, in this case, a over c, because that's the letters I happen to stick in there. So in this case, the horizontal asymptote is just y equals 3 over 1, just y equals 3. If the degree of the numerator is bigger than the degree of the denominator, then there is no horizontal asymptote.